Hi, I'm Don Welch, Director of New Business Development at MTI Instruments. In this tutorial, we're going to talk about a capacitance-based thickness system for measuring non-conductive materials such as glass, plastic, and sapphire wafer. The digital Accumeasure, in conjunction with a PC, pretty much makes a complete thickness system. The components that we have here that you need are the digital Accumeasure, which is a capacitance amplifier. It's 2 channels. Then we need 2 probes. We have here are shorter. And we need a fixture to hold the 2 probes so that they're facing each other, and we can put our targets in between the 2 probes. It needs to be a fairly rigid fixture, and this is something you can build yourself or have a system integrator build for you. Over here to complete the system, we have just a regular PC laptop, and this PC laptop runs the digital Accumeasure basic software, and that allows you to make the thickness measurements, to be able to record your data and see with a very high degree of accuracy directly in engineering units the thickness of your target. For measuring the thickness of dielectric materials or non-conductive materials, the first thing we have to do is set the probe gaps. The probe gap. So what we want to do is to have our 2 probes specified distance apart, and that distance is going to be 2 times the range. The probes each have the same range, plus the thickness of the target, and then you're going to come in a little bit closer. Okay, after we get the program started up, what we want to do is to calibrate to 2 known thicknesses on our sapphire wafers here. What we'll use is we have a micrometer here. I've identified 2 areas, one on this wafer right here, where I've mic'd it. I got 868 microns, and I have a second wafer here. This one's 793 microns. And again, we figure that out by using a standard contact micrometer to do that. The next thing we're going to do is go to thickness calibration tab. We're going to slide our wafer under between the probes, right where the known thickness area is. We put the thickness in our calibration standard thickness window, 868 microns, and then I click calibrate thickness. So now we've got the probe offset in there for the first wafer. We can go back and double check. It's 868 point something. It's coming out 867 here. It's close enough for this demonstration purpose at this point. The next thing we're going to do, we're going to take our second wafer, which is 793, slide that between the probes, and then we're going to measure what the reading is here. We know the difference between the 2 probes is 868 minus 793. We know that, the absolute delta difference, and then what we do is we take the difference between what the wafer actually is versus what is showing here. So we divide the difference between the known thickness by the apparent thickness, and that gives us our new slope factor. In this case, I've already done that, and we know that the slope factor for sapphire is 1.15384. So the next thing we're going to do is we're going to go to user calibration window. We're going to read the current slope factor, which is 1 from our original calibration when the unit was calibrated in MTI. And our slope and offset is 1 and 0. What we're going to do is we're going to change these to the new slope factor. So what I do is I double click on this and I key in the sapphire slope factor, 1.15384. That's entered in the channel 1 and channel 2 for both probes. 1.15384. Once those are keyed in, we click on the Save New Factors button. So our new slope factor is now saved to the system. We're then going to go back to the thickness calibration window. We're going to put our first wafer, which was 868 microns, in between the 2 probes. I got to make sure I get that centered correctly. And then we're going to hit calibrate thickness. Once we do that, we're all set, we're good to go. We go back to reading thickness, and you can see that I'm reading the thickness of the wafer, 868. Let's take a look at this one here, is 793. We're going to slide that under there, and we're reading within 0.2 microns of 793, 792.8. I also have another smaller wafer here from another manufacturer. This one's 457 microns. It's a little tough to see because it's clear. I'm sliding that under there. And we're reading 459 microns. And these, interestingly enough, these sapphire wafers, which look totally flat, actually have about a 2 to 3 total thickness variation over the surface. And that's what the manufacturers are actually trying to see. They want to find out if there's a lot of variation across the surface in the wafers, because these things get turned into LEDs, and that kind of difference, or a difference of 10 microns, could be the difference between a good LED and a bad LED. So I have another sample here. This is 145 microns. We'll slide that under. This is reading 147, so it's within 2 microns. We have another sample here. This one is 153 microns, and we're reading 152. So with plastic samples like this, accuracies of within 1 to 2 microns is considered pretty good. We can get higher accuracy if the samples were have higher accuracy themselves, and it's a function of cleanliness, the waviness on the plastic samples, and on these there's also little divots and dings and things that have been on these from shipment and handling. Okay, next we're going to measure Gorilla Glass. The manufacturer of the glass was kind enough to give us the thickness, but the accuracy is only to, in this case, probably about 10 microns, because they don't go past the second digit on these. So I've already set up the slope factor. I've checked it before. What we do is we put the first sample under here, and we've entered that sample thickness in here, and then calibrated on that. So every time you start with the known slope factor and a sample, you have to calibrate the sample to the system, and that's fairly easy to do. You just take one known thickness and you go in and you go to the thickness calibration tab, as we've seen before, enter that. So I'm reading 700 microns for this sample. The manufacturer says it's 700 microns. We're going to look at next a 550 micron sample. And we're reading within 3 microns of that sample, which is well within the accuracy of what they're stating on their envelope here. And we'll take a look at one more sample here of the glass. This one is 0.4 microns, sorry, 400 microns, and it's reading right on. So what we've seen here in this tutorial is that we can measure a variety of different non-conductive materials, such as sapphire wafers, plastic, which could be in process, and we've also looked at Gorilla Glass, which is, again, is a dielectric and non-conductive material. And we get very good accuracy with what we're seeing here. It's within 2 to 3 microns of what it's supposed to be, and if you're very careful with the cleanliness and setup, you can get down to typical accuracies of less than a micron. So, to recapitulate, in order to measure dielectric materials, the items that you need are an MTI digital Accumeasure. This is a D202 unit, which means it's 2 channels, and it's set up for 180 phase difference between the 2 probes here. The next thing you're going to need is to select probe sizes for your range. In this case, we used ASP 300M for metric -CTA. That means it has a connector on the back, and this probe has a base range of 300 microns, but we also have range extended it out to just about 1 millimeter. So that means I can get easily a 2 millimeter gap for inserting our dielectric materials. The other thing you're going to need to do is to have a fixture to hold the 2 probes opposing each other. This is something we made from MTI materials. This is part of a Proforma 300 deck, and the rest is just scrap metal that we machined to be able to hold the probes. What's important here is that the probes must be exactly coaxial and perpendicular to each other for high accuracy readings. On our website, we have application notes for how to do this in a little bit more detail. It talks about the calculation for measuring slope, which is actually quite simple. The 3rd or 4th graders should be able to do this type of calculation. We also have other information about measuring the dielectric materials, different probes. So check our website and give us a call or contact us by email if you'd like to buy a system for measuring thickness.